Hello and welcome to the MOOC on optical communications. In this module we discuss response time of a photodiode first, a very brief idea of what limits the bandwidth of the photodiodes, which is the response time, which is determined by the response time, and then we will discuss couple of noise processes in photodiodes, both PIN as well as APD structures, and then see what would be the signal to noise ratio if you use these photodiodes into making into a photodetector circuits or an optical receiver circuit. Now, if you recall the structure of a PIN photodiode, you have a P region, you have an N region, and then there is in between an intrinsic region which is usually quite wide, because the objective of the intrinsic region is to absorb as many photons as possible. So, you have a wide intrinsic region to which the photons are supplied, and these photons are absorbed by the material and the photocarriers are generated, that is electron hole pairs are generated. There is a strong electric field in the region, this is true for both PIN as well as for the APD structures, and what happens when you have a strong electric field is that holes and electrons will move in the opposite directions. Of course, each electron hole pair moving in the opposite direction would constitute one electron pulse, one current pulse if you would think of, right. So, as these charge carriers move, what is the distance over which they have to move? The worst case scenario is when the electron hole pairs are generated at one of the edges between IN or PI regions. Why is that so? Because if you imagine that this is the PIN region, at this edge if you have an electron hole pair generated, hole, for example, if it is onto this side, if it gets attracted to this side, has very little distance to propagate. So, it quickly propagates out. However, for the complete current component to occur, we have to wait until the electron moves all the way from the intrinsic region and then gets recombined over here. So, you see that worst case scenario, one of the electron hole pair carrier, it could be either electron or a hole, but it has to travel the entire length of the intrinsic width, which is usually almost close to the width of the intrinsic region that we take. The actual width will be slightly smaller because of the biasing, but that is for a good approximation one can think of the length over which they have to propagate as the entire intrinsic region. Now, when and how do these electrons or holes actually propagate? They actually propagate under the influence of the applied electric field. So, when the electric field is applied, the charge carriers actually drift, or it is just a way in which currents are generated. This drift is acquired by the electrons or the holes, which is proportional to the applied electric field. So, this is the applied electric field, which is the result of the reverse biasing of the photodiode. Okay. And then whether you are dealing with the electron or the hole, the corresponding drift velocities will depend on the mobilities of the electron or the hole, and it is, you can look at the semiconductor literature and find that the mobility of the holes is slightly smaller than the mobility of the electron. What this simply means is that electrons are faster, holes are slower, and which of those two will give rise to a larger response time? Obviously, the holes. The holes have to take a longer time in traversing, and therefore, they form the fundamental limitation. And if you think that the response time tau r is in some sense inversely proportional to bandwidth of the operation, the speed at which one can generate repeatedly these electrons and constitute a current, then this response time is more or less determined by the hole velocities or determined by the holes itself. So, you can have a very good idea or a very nice approximate value for the response time and write this as the width of the intrinsic region. So, maybe we will write down Wi just to denote the width of the intrinsic region divided by the drift velocity of the hole. So, the whole response time is VDH, and this kind of puts out the ultimate limit in terms of the bandwidth of the photodetector. Okay. If you look at the optical input, so for example, if you supply an optical input that looks like a nice pulse here with very small rise time, you can generate these optical pulses by various processes. You can actually modulate a continuous wave laser to generate the optical pulses, or you can use mode locked lasers to generate these optical pulses. these pulses have a very small rise time, okay. And if you give this optical pulse as input to the photodetector, okay, or the photodetector circuit, and observe the current waveform that is generated as the result of this optical input, you will see that the current is not exactly following the optical input, okay, the shape of the optical input. Initially the current rises very quickly, okay, and then there is a very slow process and then it drops off later on, okay. So, this initial fast process, okay, so this region is the fast process that we have, okay, followed by a slow process is because the fast process actually happens due to the drift, whereas the slow process is because of the diffusion. And so, diffusion, this is slow, fast is because of the drift. Drift is for both electrons as well as holes, and this occurs in the I region or the intrinsic region. However, diffusion is the one that occurs in the P and N regions that are associated with that, because these form the minority carriers and these minority carriers have to diffuse into the next junction, you know, to the adjacent region, and this process which is happening at the junctions is slower compared to the drift, because drift is because of the applied electric field and therefore it is considerably faster compared to diffusion. Diffusion is because of the concentration gradient, okay. So, in that way you have a fast process and then you have a slow process, which eventually, you know, contributes to the limitation of the speed at which you can operate this photodiode, okay. Now, what can you do in order to reduce the response time and increase the bandwidth? Well, one can eliminate one type of the carriers. So, one can work only with the electrons or the holes, but then you are not really utilizing a semiconductor material there. So, it is kind of out of scope solution for us. The other solution that you can try is to reduce the intrinsic region width Wi. But remember, Wi makes a major appearance in defining the quantum efficiency, the external quantum efficiency, which is defined as the rate at which photocarriers are generated to the rate at which photons are incident, depends on how much optical power is absorbed. But this optical power that is absorbed depends on what is the width of the intrinsic region, because the absorbed power is proportional to e to the power minus alpha, where alpha is the absorption coefficient of the material, times Wi. So, if you reduce Wi, you do not have good thickness or a length of the intrinsic region so as to absorb the photons. So, some photons might simply be not absorbed and pass on and onto the other region and they just go away. So, you are basically reducing the quantum efficiency. We will later see that quantum efficiency is directly proportional to the sensitivity of the photodiodes, okay. So, how low optical powers can be detected depends on the quantum efficiency. So, if you reduce the intrinsic width, then response time decreases, bandwidth increases, response time decreases but the bandwidth increases, but this comes at a price of reduced quantum efficiency, something that you would not want to have when you are detecting low optical powers, optical light at very low optical powers. So, there is actually a trade off between the two, and there is essentially optimum that one normally says, okay. So, you have photodetectors with larger bandwidth but reduced quantum efficiency, or photodiodes with very small bandwidth and increased quantum efficiency. This latter case, you know, where you have a reduced bandwidth typically in tens of megahertz, but very high quantum efficiencies are actually used for detecting very low optical power signals, such as a photon counting circuit utilizes this fact. So, you have a smaller bandwidth but a larger quantum efficiency. Okay, that brings us to an end on response time of the photodiodes. We will now quickly jump over to noise processes in the photodiode. Okay. You might think that there might not be any noise when the photodiode is not illuminated. If you do not shine on a photodiode, you think that there will not be any noise. But sadly that is not really the case, because photodetectors kept on a room temperature has a significant thermal energy, the materials have significant thermal energy, the atoms have significant thermal energy, and occasionally one of these electron hole pairs might be generated. And if you have reverse biased the photodiode, which you are going to do for the photodiode operation, these generated electron hole pairs will then accelerate and constitute a current. No photon but current. This is called as the dark current, and dark current is a very difficult quantity to pin down because it depends on the device structure, depends on the room temperature, and hence what would be the temperature cooling facilities that you can. The general rule is that the lower the temperature or a cooled photodiode will have lesser dark current, okay. But it also depends on the casing, depends on all kind of other factors. So, it is usually something very difficult to theoretically explain, but you can find photodiodes with dark currents typically in the range of nanoampere. Worst photodiodes are in the range of microamperes. These days you get very good photodetectors with dark currents as low as picoampere to femtoamperes. Okay, so it's this component is kind of quite negligible when you are working with very good photodiodes, especially at telecom applications. You now are able to obtain picoampere dark current photodiodes. Okay. So, this is for the dark current. There are three reasons why you get dark current, although evaluating them will be kind of very difficult. One is the diffusion of the minority carriers, which is generated because of the thermal agitations. Okay. As I said, thermally agitated electron hole pair, thermally generated electron hole pairs will drift under the application of the reverse bias voltage, causing a minority carrier diffusion current, which causes dark current. Okay. There are also other processes such as generation recombination happening, okay, and this generation recombination in turn gives rise to a certain current density or the dark current component. Finally, the surface is not very nice because it kind of creates avenues for which electrons can be generated, resulting in the form of a surface leakage current. Okay. So, this would be the surface current of a surface current component of the dark current. Please note that these are all densities, okay, which means that if you want to find out what is the current, current is given by density times area of the photodiode. So, one way in which you can reduce the dark current is to reduce the area of the photodiode, but go back to our earlier problem, reducing the area, especially reducing Wi, would again cause problems, right, because your absorbed photon power would be reduced and hence you would not be able to get very good quantum efficiencies. Okay. So, that is typically the dark current. Now, if you go to APDs, which is the avalanche photodiode, you see that we have already discussed avalanche photodiodes and they differ from regular PIN photodiodes in the sense that you actually have what is called as a multiplicative gain. This simply means that in an APD, once you generate an electron hole pair, these electron hole pairs will impact ionize the material, right. So, they will go and hit the material, creating ionization, resulting in generation of extra electron hole pairs, right. So, quickly a pair of electron hole pairs can generate a million number of electron hole pairs, leading to an internal gain of the device. So, there is no amplifier connected, but there is an internal gain of the device, right. So, this multiplicative gain is denoted by the parameter m, and this m in turn consists of the multiplicative gain because of the electrons alone and multiplicative gain because of the holes alone. Okay. These factors Mn and Mh can be obtained from some theoretical analysis, which is kind of very difficult to do in this course. So, we are not going to look at that one, but briefly the idea is that if you evaluate Mn by assuming pure electron injection and you determine Mh by pure hole injection, and then look at the concentration gradient of the holes or the electrons. Okay. So, concentration gradient is dJ by dx. So, if you look at the concentration gradients and calculate these, relate these to the densities Jp and Jn of the hole as well as the electron currents, plus whatever the generation generation rate that is happening inside the photodetector, these two are essentially functions of all these parameters. Okay. And you can, it's kind of little difficult to do the exact analysis because this analysis has to be different for different kind of structures of the APD. So, normally what we assume is that there is essentially a homojunction kind of a device, so that the multiplicative gain is assumed to be for simple analysis it is assumed to be not statistical, it is assumed to be kind of a deterministic process, and you assume that all the optical power that is incident on the APD is completely absorbed. Okay. So, you do all that to evaluate Mn and Mh. What is interesting in this Mn and Mh is that depending on the ionization parameter, if electrons have a propensity to ionize more compared to the electrons, then Mn will be larger than Mh. Okay. So, depending on the parameters you can either have Mn larger than Mh or you can have Mn smaller than Mh. Okay. And for a good APD, we normally try to maximize one of those with respect to the others, which means that the injection or the impact ionization happens mostly because of one type of the carrier whose impact ionization is larger. So, if you have electron impact ionization is larger, you try to make APD in multiplication region mainly consisting of the electron impact ionization. Okay. So, these are something that are little advanced for the course to discuss. So, we are not going to look at that one, but associated with this Mn and Mh there is a photocurrent. If you look at the photocurrent, you will see that the photocurrent itself is not really a constant photocurrent for a constant optical input, but there is actually a fluctuation of that, and this fluctuation is because of the multiplication process that is fluctuating. Okay. The variance of this fluctuation process is given by, so there is an effective M that goes along with this one. Okay. So, there is an effective M that goes along with this Mn and Mh, and then you have the fluctuation of the current itself given by 2q IP0, IP0 is the primary photocurrent that is generated, times M square and F. M square is the multiplication square, multiplicative gain parameter square, and F is what is called as the excess noise factor. Okay. So, this excess noise factor is actually a function of M itself. So, making our APDs little more complicated, their excess noise factor itself depends on M. If you look at the excess noise factor as a function of the multiplicative gain, you will see something like this. So, this would be the way in which this goes. For there is another parameter called k, which I will just define in a minute, but if you change this k, you will see that there is actually a linear increase. So, as k parameter increases, k is a constant which increases, which depends on the ionization parameters of the electrons and the holes, and as k increases, the excess noise increases for the increased in multiplication factor. Okay. So, they are actually related like this. Multiplication factor is basically how much photocurrent you are able to generate given what is the primary photocurrent IP0, whereas the excess noise factor is given by M times 1 minus k. As I said, k is a constant which depends on the ionization parameters, and M minus 1 whole square divided by M square. So, you can see that this excess noise factor is actually a function of M. Okay. Now, this is all about the APD. We will come back to this equation slightly later. Okay. For now, we will look at other noise processes that are there in the photodiodes. Okay. Other noise process that is there in the photodiode, and that noise which is very important is called as the short noise. Okay. Suppose you take an ideal light source, an ideal laser, and then you give it to an ideal photodetector. Okay. So, this is an ideal photodetector, right, and this photodetector simply responds by generating one electron hole pair whenever it absorbs one photon. Now, you expect if you keep the photon numbers constant, that is to say if you keep the photon flux to be a constant value, right, it is like a continuous wave power that you are giving, you expect the current also to be just a continuous line, it is like a DC input and a DC output is what you expect, right. But unfortunately that does not happen, because even an ideal laser when it is operating above the threshold does not send photons in a regular manner. So, this is what you expect, each photon coming in, and therefore, if you actually look at time axis and then divide time axis into intervals of t duration, then see the number of photons here, you expect the number of photons to be the same here, right. So, you expect at each interval t, you expect the number of photons to be the same, but unfortunately that is not what happens. What happens is that the photon flux, which is basically defined as the number of photons divided by the time interval t or per time t, there is actually a distribution of the flux itself. It is not constant, but there is a mean photon number, which means in some time slots you get n1, some time slots you get n2, in some time slots you get n3, you get n4, and if you do an average of this one, there will be an average photon number nph around which photon numbers are fluctuating. Okay. There is no this one for this is actually quantum mechanical in origin. This is the nature of light. Okay. The nature of the light, which does not allow photons to be in a very regular manner, is built into light itself. So, you can't do anything about that. However, what is the effect of this statistical distribution on our photodetector? Well, in some time units you are getting n1 photons, therefore, n1 electron hole pairs are generated or proportional to n1. So, n2 photons are incident, proportional to n2 number of electron hole pairs are generated, and so on, right. However, there is one more story into this. The electron hole pair generation, that itself is statistical. It with a efficiency of eta or with a probability of eta, if you normalize it appropriately, electron hole pairs are generated. The probability that photons are incident, but electron hole pairs are not generated is 1 minus eta. So, there is a statistical distribution in the way electron hole pairs are generated in the photodetector. There is a statistical distribution in the way photons are coming in into the photodetector itself from the laser. So, there are the effect of these two is that the current distribution becomes essentially statistical. Okay. So, if you look at the current pulses, in some duration you might generate 3 current pulses, next time you might generate only 2, next time you might generate only 1, then there are 3 or 4 like this. So, there is essentially a statistical distribution in the way current pulses are generated, and this statistical distribution follows what is called as Poisson's distribution, or very closely follows what is called as Poisson's distribution. What is Poisson's distribution? Suppose you are looking at the number of photons that are generated in one time unit, okay, you call that as probability of n photons being generated. This is given by e to the power minus nph, which is the mean photon number, and the mean photon number to the power n divided by n factorial. Okay. For large value of n, this essentially approaches Gaussian distribution, but for small values of n, which happens when the optical input power is low, the statistics is actually Poissonian. I mean, it is actually Poissonian everywhere, but for large n you can approximate it to be Gaussian. Okay. As we said, this process is also the same as the electron hole pair generation. Okay. So, the combination of these two statistical nature is that your current is not really a constant, but there is actually a distribution around this current, okay, with a mean photocurrent given by the mean value of the photocurrent, and there is actually a time varying component, which we can write this as delta IPH of t, which has 0 mean, okay, but a variance which we call it as short noise variance, given by, surprisingly it is also given by q into IPH. So, it is actually directly proportional to the mean photocurrent. So, you might actually think that, oh, increasing the photocurrent value, mean photocurrent value will increase the short noise variance, and you are right, short noise variance does increase and increases linearly with the increasing photocurrent. Okay. However, what you are interested is not just this one, you are interested in what is the total noise power contributed into the photodetector circuit having a bandwidth BE. So, let us say this is the power spectral density. The power spectral density is essentially constant, and therefore, this is a white noise process. The value of the power spectral density is q into IPH. However, if you now put in a band pass filter, okay, whose bandwidth is BE, the low pass bandwidth is BE, right, the total power contained within this bandwidth will be given by 2q IPH, which is the mean photocurrent, times BE. Okay. So, this is your short noise variance. Okay. This is the variance, because variance is actually power that is dissipated across, average power that is dissipated across a 1 ohm resistor. In case there is short noise, then you replace this photocurrent with the mean dark current. Okay. So, the short noise variance simply becomes 2q into mean photocurrent, which is generated because of the photon incidence, and the dark current because of this, times BE. For APDs, the short noise variance is slightly complicated. It is actually given by 2q into primary photocurrent, okay, which is again mean, plus the dark current times m square, which is the multiplicative gain, times f BE. So, this excess factor, right. So, this excess factor of m square into f is because of the APD structure. Okay. So, we will stop at this point. We have looked at the noise processes in the photodiodes. In the next module, we will give a small introduction on the other noise process, which is thermal noise, and then we put all these things together to discuss the signal to noise ratio aspects of a simple photodetector circuit. Thank you very much.